let us talk about a very important concept, which is the second law of Newton, or second Newton's law. And so this is the one that talks about what a force really means. So the law states that the summation of forces, the external forces, plus all the internal forces, and we're going to mention what that means, is equal to the mass of the particle or the system, a combination of particles, times acceleration. So there's a lot of information here. This simple expression has a lot of content. So external forces are, if you remember statics, you had forces that were pushing on something like a bridge. We had forces that were holding something in place like a rope. Gravity, so gravity is an external force. And internal forces, we talked about them in statics as well when we talked about elements that we had to cut in half. Remember when we had an element that was connected to another element, and then we would say, oh, let's cut it in half and see what the forces the internal forces are. Well, internal forces are stresses, and strain is derived from internal forces. So you can have external and internal forces. Okay, so you can picture in a system, a bridge, a box, a sphere, any force that is applied to the boundary or on the boundary is an external force. Any internal displacements, stresses, forces obviously are the internal forces. Okay, for this equation to be as simple as this, we simply say all the forces, capital F, which is a vector, we know that by now, is equal to the mass of the particle times the acceleration, which is the second derivative with respect to time of the position. Another way of expressing that is that the summation of all the forces is equal to mass times x double dot. We talked about this before. Dot is a derivative with respect to time, and prime is a derivative with respect to space. So like if you have y prime, this means the y, the x, where y is a function of x. Okay? Alright. For this to be true, just like that, mass has, we talked about this too, mass has to remain constant. You cannot lose mass in the process, like in a combustion process or like burning something. Mass has to remain constant. Okay, so let's look at one example very quickly that we should be pretty familiar with. So in statics, we saw friction, and we basically had a case where we had a slope, and that slope had an angle. And then let's choose a different color. Say we had a box, and just for this example, the box is going to be like so. Okay. And on top of the box, there's an object. Could be a person, for instance. Okay, well, this is a car. Well, this is something that's sliding on a slope. So from statics, we learned that if the force going this way was bigger than the friction force, this was moving. If the friction on the right hand side was less than the friction force, this was not moving, was static. Also from statics, we learned that it was important, or crucial really, it was very important to have a coordinate system. And you had two options, or many options, but we typically design it like this, or place it like that, or in many cases we decided to put it like this, right? And if you remember, it's because you're going to have most of the forces parallel to those two axes, x and y. Okay, so all this should be familiar for you. So there's a slope, and there's something sliding on it, or we don't know if it's sliding. And the question is, find the position. Find the position as a function of time. Function of time. Okay, so how to know with respect to x where this position is, say the center of gravity, is with respect to mass. And this is just basically the angle with respect to horizontal plane. So the first thing we need to do is the free body diagram. So let's place my object right here and my coordinate system right here. X, Y, and then Z will be 90 degrees from these two. But you notice that a lot of times, or in most cases, we ignore Z because we say that this is going to be a rectilinear motion, meaning that it's only going to have motion in the X direction. Now, if it's not going to have motion in the Z direction, I can ignore that and make it much easier because my force vector is going to go from R3 to R2, and this is dimensions. So we can simplify one dimension. Okay, that is basically going to be symmetrical on that dimension. It's not going to, in real life, could move on a curve in X, Y, and Z because they're, and we'll talk about that when there's curvatures and when there's many dimensions, well, 3 dimensions. But in this case, we can ignore that because we're assuming that it's only going to be sliding down. And that's the other thing. When we start our body diagram, we have to start placing our forces. So let me exaggerate this a little bit more. Say like that. Okay. All right. So at the center of mass, I'm going to have m times g, which is my force, and then I'm going to have normal force because of this surface, and then I'm going to assume this is the thing though, if I'm interested in finding the movement down the hill, then my friction is going to be opposing the movement. If I'm interested in saying what's the force needed for the system to go up, then my friction will be on the opposite direction. But let's say right now our system is moving down the hill. Okay, so this is going to be my force of friction. Another thing that we're missing here is the angle. So the angle is theta. Therefore, if I extend my normal force and this needs to be parallel to x, then if you notice, this is probably the most difficult part of all this problem, is realizing that this angle theta is this angle theta. That was probably the most difficult part. And we saw that in statics multiple times. And if you want to see that more clearly, then we have that is a force, and this force, this is very cool because it's mg, this is n, and then that force will have this component here, and then because of my x and y, this thing will be like so. All right, but notice that this component and this horizontal, that has the angle theta. So this right here is the angle between this line and this line. Okay, so say this is theta. I should have used that. Let me magnify that. Let me get that a little larger because I think that this is the most important part to clarify. Okay, this is my normal. This is my plane, or actually gonna be along my friction force as well. If I extend this like so, extend this like so, we're trying to identify that there is an angle between this and mg. This is more like this. There you go. Okay, cool. Now I should have it. Okay. All right. So now this goes like that. Goes like that. Okay. So this angle right there is theta, right? Which is this angle right here. And we're trying to find the angle between this and the perpendicular to the plane. So if you want, let's remove this part so it's not as confusing. Okay, so if you notice, we're gonna have that this is theta and say this is alpha. Of course, this is 90 degrees. So theta plus alpha is equal to 90 degrees because we already have 90 degrees here. So theta plus alpha plus this 90 degrees here is 180, right? Therefore, alpha and theta are 90 degrees. Well, if we already have our 90 here, that means that this and that have to be 90 degrees as well. So alpha is going to go here, and theta is going to go here. Okay, so that's just showing that this is theta. All right, if you have questions, please reach out. But we did this many times in statics, and it's just really, this is just geometry. It's not even dynamics at this point. All right, so let me go ahead and clear some room right here and just use my free body diagram to create my forces. So normal, mg, and friction. Okay, with the with this right here being theta. Therefore, when we start building our system of equations, we can do say summation of forces with respect to z equals to the mass times the acceleration with respect to z, But we said that nothing happens there. So if this is 0, then the summation of forces equals 0, meaning that basically there's no forces on that axis. So we already decided to only worry about x and y. But this is actually completing the concept right here. Now, summation of forces in y is equal to the mass of the system and the acceleration on y. And now that should give us some information. So remember, y is on this tilted coordinate system, and we have that going up is positive. So we have that the normal force, and mg has a component going down, so minus mg cosine, because we're doing the y component, times cosine of theta is equal to mass times acceleration on y. But I don't want us to confuse y with g. So this is g, this is gravity, and actually gravity is a vector. It has components in the vertical direction. Well, in this case, we'll have components in x and y. So interestingly, because of the coordinate system that we used. But if your coordinate system is regularly x and y, then your gravity is z. Gravity is 0x minus 9.8 meters per second squared in J, 0k. Okay, so gravity is a vector. All right, so the next thing we need to do is to, well, first of all, so this is y. Yeah, acceleration across y. So if we say that is not accelerating on y because there's only one axis of displacement, which is on x, then we can say that this is 0 and this is just like statics. The summation of forces equals 0, then my normal force is equal to the mass of my system times the gravity times cosine of theta. Okay, but this is interesting because remember that the friction force is equal to the friction coefficient times the normal force, right? Remember that this is how we characterize the friction force, is the coefficient of friction, which is just a number between 0 and 1, it's a percentage, times the normal force. Remember, for instance, for a tire made out of rubber on a dry street on pavement is around 60%. So the friction force is about 60% the weight of the car. All right, so what this means is that friction is equal to a coefficient of friction times mg times cosine of theta. So we already have our friction force as well. All right, this is g. This is, I'm sorry, this is y, okay? So don't get confused. All right, the summation of forces in x, this is gonna bother me. Let's do this the right way. So this is with respect to g, to respect to y, I mean. All right, but this is 0 because it's not moving in the y direction. It is only displacing in the x direction. We already mentioned that, right? Because it's moving on the slope. All right, so summation of forces in x equals the mass of the system times the acceleration, x dot dot. And that is not 0. That is the friction force, which is negative, and the gravity component in the x direction. So the gravity component in the x direction is mg times sine of theta minus friction equals to m x dot dot. All right, but we know that friction is right here. So let's complete that and say that mg sine of theta minus, you should be able to follow me with this, it's mu mg cosine of theta is equal to m x double dot. So m cancels out, g that multiplies sine of theta minus mu cosine of theta is equal to x double dot. Now see how we read this problem. Since the slope has a constant angle, then this is just a number. Sine of, say, 45 degrees, that's a number. Mu is the coefficient. Cosine of 45 degrees, all this is a number. So really what we're saying is that the x dt is equal to a number, equals to c. But if, picture this is a, I don't know, a project where this platform has some pneumatic arms, some levers, and while, I don't know, this is like an amusement park where there's a ride and you're sliding down the slope, the hill, and this slope changes the angle, then in this case, if the angle is not fixed, if the angle varies, then this function is, in other words, the acceleration is a function of time, but also is a function of the angle. So it's not as easy, it's a multi-variable equation. In the case we have, it's pretty simple because this is just a number. These angles are fixed, are just a number. But if the angles change because of, I want you to picture what I'm saying. So when this bus moves down, and there's a mechanism that makes this slope change angle, in that case the solution is not as easy because you need to find the solution for a two-variable differential equation, multivariable differential equation. And now also picture that while you're moving, the coefficient of friction varies on different parts of the slope. Some parts are very fast, some parts are very low friction, some parts have very high friction. So in that case, this is not a number. This is also a function of something. It could be a viscoelastic coefficient, it could be a function of position. So let's say in that case, mu was a function of x, right? So the gravity is constant. Then we have sine of an angle that varies minus mu, which different positions will have different values, equals x dot dot. So this is where it's very difficult to solve. But notice that the equation is the same, the formula in the equation, the governing equation is the same way we just did it. We just set the free body diagram, we place our forces on the center of mass, and we choose one instant, and then derive everything from that instant. But then we can say, okay, but from that instant we know that the angle can change and the friction can change. The gravity is going to stay fixed, but this is the only constant. Everything else here varies. So acceleration, okay, so x dot dot is a function of time and position, because say the friction coefficient had different values at different values of x, and the theta also changes. So this equation has three variables. It's a three-dimensional differential equation. This type of equation is much more difficult to solve. You're lucky that in this class we're not going to have to solve that. But if you go for mechanical engineer and robotics and sometimes even electromechanical projects, you'll see that you'll have to find the solution for this so that you can control and predict the position and the acceleration of the system. All right, but let's go back to our equation right here, where it's actually pretty simple what we have. Now that we know that it can get very, very complicated, now we realize that it's pretty simple because everything here is constant. So the way you solve this, whoops, I'm sorry, it's second derivative right here. The way you solve this is simply by integrating. And you should know how to integrate, right? So if we bring that x dot is equal to c t, yeah, we're keeping dx on one side, we're bringing dt to the other side, right? Basically what we're doing is dx c dt, right? So we're integrating once. This is equal to 1/2, actually. Well, sorry. Let's do it by step by step. So integrating that, we get ct, right, plus another constant. So this is velocity. Let's say it's our v naught, a constant initial velocity. We saw before that this could be 0 or could be an initial velocity of 5, 10, whatever. This is a number. It could be 0 or any constant. All right. If you differentiate this again, then you're gonna have, and we're integrating, not deriving. Okay, so we integrate because we want to find the x value, the x with respect to time. So integrating this guy, we're gonna know that this is 1/2 c t squared. This is why we're confused, because this is the second derivative. So maybe what we need to do is dt c dt. Yeah, there you go. So second derivative with respect to t. Okay, so we're integrating once and we get c dt. That's why I was confused, because for a minute I was thinking there was t squared, and it's not t squared, it's the second derivative of t. So if you integrate once, you get ct. If you integrate twice, you're gonna get 1/2 c t squared. This is plus constant, then plus your constant times t, and now we're talking about position, plus an initial position, right? So here's the same thing, dt, this is plus v naught t plus x 0. Okay. So what is my constant? My constant is all this. All this is my constant, because again, we're having a fixed angle and a fixed friction. So my position at any point in time is equal to 1/2 times my whole constant, which was g sine theta minus mu cosine theta times t squared, right, plus my initial velocity times my time, any instant in time, 1 second, 1 millisecond, 1 hour, whatever I want to find, plus my initial position. Could be at 0 meters or at 10 meters, whatever I want. So this is the solution for the position as a function of time for this for this example, for this case. Now, whenever they give you this type of problem, you know how to solve it. The angle could be whatever number, 45 degrees, 30 degrees, whatever. The friction could be whatever number. You know how to set up your coordinate system. You know how to set up your body diagram. And you know how to do your system of equations. And x and y and z and y is going to be zero acceleration, but in x you're going to have some acceleration. And that is indeed the equation that you're going to have to solve, a second order linear differential equation. That second order linear differential equation has this solution, which I'm sure you're seeing in physics. Actually, this solution is a general case, but you saw specific cases in physics, and that's where it comes from a second order differential equation, which is the acceleration. And if you want to know the acceleration, it's very simple. You just simply have to know your constant value. If you want to know your acceleration as a function of time, at any time, you just plug these values here, and you're going to get the same acceleration. But if you want to know your position, you simply solve for this equation where, again, this is a constant.